As can be seen in the strange shapes covering this region, these cell-like formations reveal the secret of Pluto's heart because they are the signatures of a process called convection, which appears everywhere a fluid is warmed unevenly, from the sun to a boiling kettle. Evidence of convection means that something underneath Pluto's heart is warmer than the surface and is causing this great plain of frozen nitrogen to slowly churn over the course of possibly millions of years. And if you look closely, you will notice that the icebergs are all generally gathered around these convection cells because they are likely being pushed to the edge by the forces below. Before New Horizons visited Pluto, we only had limited knowledge of what its surface looked like. Now we have seen it in all its wonder and glory. We have discovered many of its fascinating features, some of which we explored today. Every time you take a look at Pluto, it seems like something new can be found. And Pluto is just one of potentially hundreds of dwarf planets in this region called the Kuiper Belt. Can you just imagine the wonders that exist on the other dwarf planets that we haven't visited yet, such as Haumea, Makemake, or Eris, for example? One day, hopefully, we will see them in all their frozen glory as well. I hope you enjoyed this video. If you did, then why not watch another? There is plenty to choose from. Thank you for watching, and I'll see you next time. NASA, meanwhile, has successfully worked a big problem. Its engineers had sent a wrong signal to Voyager 2 and had lost contact for nearly about 10 days. Engineers sent a wrong signal to Voyager 2, and now the space probe is on its own at a distance of 20 billion kilometers. Launched by NASA in 1977, Voyager 2 stands as one of humanity's greatest space exploration achievements. More than 40 years later, the spacecraft continues to transmit data as it journeys through the vast expanse of space. What discoveries has it made over the decades? With no plans to stop fueling human curiosity, Voyager 2 keeps driving our quest for knowledge about the solar system and beyond. Now let's venture to the outer reaches of the solar system as we approach the heliopause, the boundary of the sun's influence. Let's take a moment to understand it. The heliosphere, a protective bubble created by the sun, consists of charged particles known as the solar wind. The interstellar medium, which is made up of particles from stars and other astronomical sources, is where these particles eventually meet particles from outside the solar system after traveling deep into space. The heliopause is the point at which the solar wind is no longer powerful enough to push against the interstellar medium. It resembles the edge of the sun's bubble. In November 2018, Voyager 2 crossed the heliopause for the second time, after its twin, Voyager 1. The heliopause is a line where the interstellar medium, or substance that fills the space between stars, and the solar wind, or charged particles released by the sun, meet. Voyager 2 saw a dramatic decrease in solar wind particle density and an increase in interstellar particle density when it passed this limit. This verified that the spacecraft had left the heliosphere, the bubble-like area where the sun's effect is most noticeable. Voyager 2's passage through the heliopause provided valuable plasma density measurements thanks to one of its unique operational instruments. Plasma, the electrically charged gas in space, was analyzed, revealing a key difference between interstellar space and the heliosphere. Unlike the plasma within the heliosphere, Voyager 2 found that interstellar plasma is significantly denser, offering scientists a deeper understanding of the environment beyond the sun's influence. This discovery was particularly important because Voyager 2's plasma instrument remained functional at the heliopause, allowing for direct plasma density measurements, something Voyager 1 was unable to achieve. The sharp increase in plasma density confirmed that the interstellar medium is denser than the solar wind. Our knowledge of the transition zone and the relationship between the heliosphere and interstellar space has improved as a result of this data. Observations of magnetic fields and high-energy particles, known as cosmic rays, are produced when stars explode and other significant galactic events take place. The Sun's solar wind serves as a shield inside the heliosphere, limiting the quantity of cosmic rays that can reach us. Voyager 2 discovered much more cosmic rays after it passed over the heliopause, demonstrating how the heliosphere shields everything within it, including Earth. The magnetic field near the solar system's boundary was also measured by Voyager 2's equipment. It's interesting to note that the spacecraft saw that the interstellar magnetic field's direction resembled that of the Sun's, indicating some degree of connection between the two. This discovery opened up new scientific possibilities by casting doubt on some preconceived notions about the boundaries of interstellar space. In the end of the Sun's influence, energetic particles and cosmic rays, Voyager 2 saw a significant shift in the behavior of cosmic rays, which are high-energy particles that come from outside the solar system, as it moved into interstellar space. The solar wind plays a partial role in shielding the solar system from cosmic rays within the heliosphere. However, Voyager 2 detected a higher intensity of these particles beyond the heliopause, confirming the heliosphere's role as a barrier against cosmic radiation. The observations also revealed that the heliopause is not a fixed boundary, but a dynamic and ever-changing region. This breathing effect results from the heliosphere's expansion and contraction in response to solar activity. These findings suggest that the boundary is highly irregular and emphasize the complex interaction between the Sun and the interstellar environment. Upon crossing the heliopause, Voyager 2 entered interstellar space, providing a unique window into this vast and unexplored region. Voyager 2 crossed the heliopause and began examining the characteristics of the interstellar medium, contrasting it with the solar wind's hot, low-density plasma. It discovered a chilly, dense plasma environment, providing a unique window into the interstellar medium's characteristics and revealing hints about the galaxy's genesis and development. This discovery aids our comprehension of the Sun's protective bubble and its interactions with the surrounding environment. Such information is crucial for understanding the universe beyond our solar system and for future space missions, akin to identifying the galaxy's neighborhood boundary and glimpsing the cosmos beyond. The moment Voyager 2 crossed the heliopause was momentous, signifying its entry into interstellar space and exit from the solar system. Despite being billions of kilometers away from Earth, it continues to transmit valuable data, deepening our understanding of the interstellar medium. Crossing the heliopause is akin to stepping into uncharted territory, marking the boundary of the solar system. Its observations of interstellar space and cosmic rays within the solar wind have transformed our perception of our place in the universe. Launched decades ago, this small spacecraft remains a source of amazement as it ventures into the unknown. Voyager 2's discoveries at the edge of the solar system will play a crucial role in shaping future exploration, providing a foundation for studying the interstellar medium and the interactions between stars like our Sun. Upcoming missions, such as the Interstellar Probe, seek to build on Voyager's legacy by traveling even farther into interstellar space. Both Voyager spacecraft are equipped with the same set of instruments, including cameras, magnetometers, and plasma detectors. However, over time, the way these instruments operate has evolved. To conserve energy for other instruments, Voyager 1's cameras were turned off after completing its planetary mission, preventing it from capturing images during its interstellar journey. Since Voyager 1 could not directly measure the density and temperature of interstellar plasma, Voyager 2 provided crucial data with its operational plasma instrument during its heliopause crossing. Both spacecraft also carry golden records, phonograph, records containing sounds and images that represent the diversity of life and culture on Earth, intended as a message for any extraterrestrial beings they may encounter. These records serve as a time capsule embodying humanity's curiosity and aspiration to connect beyond our solar system. Despite being identical, our knowledge of the solar system and interstellar space has been revolutionized by Voyager 1 and Voyager 2. Taken together, from the structure of the heliosphere to the dynamics of planetary atmospheres, their data has helped scientists make many discoveries. As they continue to function well beyond their anticipated lifespans, they also represent human ingenuity and the spirit of exploration. Although they have traveled distinct routes, the twin spacecraft, Voyager 1 and Voyager 2, are both dedicated to exploring the universe. Voyager 2's extended planetary mission and operational plasma instrument have offered unique insights into the outer planets and the border between the solar system and interstellar space. Even though Voyager 1 was the first spacecraft to traverse interstellar space, collectively, they have given humanity a better knowledge of our position in the cosmos and motivated countless generations of scientists and adventurers to keep aiming for the stars. For over 4 decades, Voyager 2 has been exploring the cosmos, delivering groundbreaking data about the solar system and beyond. Even after its historic flybys of the planets and its entry into interstellar space in 2018, Voyager 2 continues to send valuable information from billions of kilometers away. Despite its age and extreme distance, scientists remain hopeful about the discoveries Voyager 2 will make as it journeys further into interstellar space. One of its key scientific goals is to create a detailed map of interstellar space. Researchers are particularly excited to learn more about the interstellar medium, the substance that fills the space between stars. As Voyager 2 moves deeper into this uncharted region, its instruments are perfectly designed to examine the density, temperature, and composition of the medium, which consists of interstellar dust, plasma, and cosmic rays. By comparing data from Voyager 2 with its twin, Voyager 1, researchers may develop a more detailed picture of the interstellar environment and how it interacts with the heliosphere. Experts seek to better comprehend the heliosphere's form and behavior. The heliosphere, the bubble-like zone formed by the sun's solar wind, protects the solar system from many cosmic rays and interstellar particles. The voyage of Voyager 2 offers a unique chance to investigate the behavior and evolution of the heliosphere. The shape of the heliosphere, which seems uneven based on Voyager 2's measurements, is of special interest to scientists.